Alright, so we're about to finish up our Unit 1 over the motion of objects by talking about one last thing that has to be considered when we're analyzing moving things, and this is the idea of momentum. You can see here I've written this wall of text to give momentum a definition. It is kind of hard to define, but I think it does make a lot of good common sense. I've defined momentum here as a quantity, that means amount or measurement, so a number, an amount that describes quote-unquote how much motion an object has when we take into consideration the object's size and how fast it's going, the velocity of the object. We'll talk about this later on, that it's a conserved quantity, it can be transferred back and forth between objects. And down here I've written an equation. So let's talk about the important parts of this definition. It's a quantity, it's a measurement. It describes how much motion an object has, considering the size and velocity of that object. So you can see down here in my equation, this P is the letter that we're going to use to represent momentum. And very, very simply, it's equal to the mass of the object that you're analyzing times its velocity, mass times velocity. Mass is going to be measured in the unit of kilograms, and velocity, of course, is meters per second. So you combine that unit, the unit for momentum is kilogram, meters per second. Kind of a strange unit, but that's what it is. The idea here is that if you're talking about the motion of an object, it is not quite enough to just know the object's velocity. Say that I have a large rock and a small rock. And let's say that both of these get thrown with a velocity of 2 meters per second. Now, I know this is kind of a silly question, but which stone would you rather get hit with? Which one would you rather be hit by? I think we would all agree the small one, because it's going to deliver less something. Yeah, this is related to the idea of force. The smaller one is maybe going to strike us with a smaller force. But a simpler way of thinking about it is that the smaller one really has less motion. There's less stuff moving. Even though they're both moving at the same velocity, there's less stuff with the smaller rock. So we need some way of talking about that idea, that larger objects that move are carrying with them more motion. A larger quantity of motion. Smaller objects, we have less stuff moving, so they're carrying with them a smaller quantity. So the velocity is not enough to talk about motion. We also have to bring in the size of the object. And this gets us the idea of momentum. Momentum is the product, what you get when you multiply mass times volume. The mass times the volume will give you this quantity called momentum. So really simply, let's say that this object has a mass of 2 kilograms. Let's say that this stone has a mass of 0.5 kilograms. We could find the momentum of these very, very easily. We could say that the momentum of this first one, P1, is very simply going to be the mass times the velocity, 4. And don't forget our units, kilograms, meters per second. The mass of this second object, here's object 1, object 2, the momentum of the second object, mass times velocity, you can all see that's going to be 1 kilogram meter per second. So it's very, very clear and obvious that we would much rather be on the receiving end of this smaller momentum as opposed to this larger one. So momentum is important for us to consider when we're analyzing the motion of objects, as we've been doing in this whole unit. It's a quantity, it's a product of how much stuff you have and how fast is it moving. Momentum. Let's go on to talk about this second idea of momentum, that it is conserved. What does that word conserve mean? Well, it means it's never wasted, it's never lost. You can't really add any more to it. The momentum of a system, remember a system is whatever you're studying, the momentum is always conserved. So the total momentum of a system cannot change. It simply gets transferred between objects. Now you may be thinking this sounds a lot like energy. For those of you who've studied energy before, energy is not created or destroyed, it's conserved, and it's transferred between objects. And yeah, that's true. This is actually closely related to the idea of energy as well. So let's go on and be a little bit more specific about this whole conservation of momentum idea. Okay, so here I have an example of conservation of momentum using the exact same ideas earlier. Here we have two, this time I'm calling them spheres. So our system, what we're studying is very simply two spheres flying. For simplicity's sake, let's just imagine they're flying through empty space. So they're flying directly towards each other. This first sphere is going with a velocity of 2 meters per second to the right. Its mass is 2 kilograms. This object is moving at the same velocity, 2 meters per second to the left. Uh-oh, I hope that you caught something that I forgot. This velocity should be what? It should be negative, right? Why is that? Because velocity is a vector. We're not only worried about the size, the 2 part, we're also worried about the direction. This thing is moving to the left. How do we denote that? With a minus sign. So this velocity over here is a positive 2 meters per second. This one is a negative 2 meters per second. And this one is much smaller. It has a mass of 0.5 kilograms. So remember what I said earlier. The conservation of momentum says that the momentum of the entire system, not just one of these objects, but the entire system, the total momentum I have here in my system cannot change. It cannot increase, it cannot decrease unless acted on by something else outside the system. But if I'm analyzing just these objects, the momentum of this system will not change unless there's something else coming from the outside, unless I interact with one of these and give it a push or a pull, or unless another sphere comes in or something like that. But as long as I have these two spheres, their total momentum cannot change. Conservation of momentum. So let's say that they are on a collision course. They're going to collide with each other. And I want to know what their momentum is. What is the momentum of the system of both of these spheres? Well, you can see here I've made a little equation. The initial momentum, that's the momentum. Remember, P is momentum. The momentum before the collision is very simply going to be their momentums added together. The momentum of object 1, so I could say the momentum of object 1 plus the momentum of object 2. And you can see here I've kind of expanded that. Momentum we know is mass times velocity. So the mass of object 1 is 2 kilograms. The velocity is 2 meters per second. So that's going to give me the momentum of my first object in the system. To find the initial momentum of the entire system, I've also got to add together to that the momentum of my second object, m2 v2. The mass of the second object, 0.5, times its velocity, negative 2 meters per second. So let's start plugging things in here. The mass of object 1 is a 2. The velocity of object 1 is a 2. What do I do to those to find its momentum? I multiply them together. I find their product, so I'm going to get a 4. Plus the momentum of object 2. Its mass is 0.5. Its velocity is negative 2. Multiply those together, find their product. That's how I find its momentum. Its momentum is going to be negative 1. Before they collide, the initial momentum, adding up the momentum of the two objects in my system. I want to know the total momentum of the system before they collide. Add up the momentum of the two objects. That's going to be 3 kilogram meters per second. Well, what if I asked you, what is the momentum going to be after those objects collide? The momentum after the collision. We could call that PF. Well, think about it. Momentum is a conserved quantity. It cannot go away. It cannot dissipate. I can't add more momentum out of nowhere unless I have some other object interacting with my system from the outside. I don't have that happening. So the momentum of the system itself cannot change. So the final momentum after they collide together is still going to be 3 kilogram meters per second. Now there are so many interesting things we could do with this. We could talk about the center of mass of these objects and how it's moving. We could predict after they collide, after the collision, we could predict their new velocities after they've exerted a force on each other and swapped some momentum. But we're not actually going to do that because you have to know some more about energy and you have to have some more mathematical skills. So this is going to be the simplest that we're going to do, is just predicting the momentum after objects interact. And you guys just need to know that, hey, momentum is conserved within a system. So the initial momentum is going to be equal to the final momentum. If you're interested in learning some more of those complicated ideas involving predicting their new velocities and things like that after objects collide, then you're more than welcome to talk to your instructor, things like that. Like I said, that involves some mathematical skills that are just slightly advanced, really not that bad, and it also involves knowledge of energy. And we are going to talk about energy actually in the next unit. But this is all we're going to do with colliding objects. You need to be able to predict the momentum after an object collides.